So good morning. Now we are discussing elliptical cryptography. So here this is one of the way of representing elliptical. So it is EQ of A comma B. That is how we are going to represent that pi square of mod Q is equal to x Q plus AX plus B mod Q. So when you are trying to represent it with a prime number, so that is E to the base 23 of A and B which are constants. So this is how we are going to represent a particular elliptic curve equation, right? On this you have to generate a point G. So G is a point that you are going to find on the elliptic curve with large number of n. So how you are going to find out this particular G and this particular n is an important point in the elliptic curves. Okay. So I have taken G of pi comma 1. If you represent this G of pi comma 1, that is pi comma 1 on x and y, which means pi you are going to represent on x and 1 you represent on y. So if LHS is equal to RHS, you can say that this point is on that curve. Okay, so you have to take a generator point in such a way that the point has to be on the elliptic curve. So I have taken pi comma 1, which is the point on the elliptic curve, E23 to the E base 23 1 comma 1. So here for this particular G, I have to find what is n. So how to find a particular value of n with this particular generator point? So we have to start doing 1G, 2G, 3G, 4G, so on until you get 28G is 0, 0, which is point of infinity. So once you get point of infinity, we will end the process and that we will represent it with n is equal to 23. So this is how you are going to find a particular generator point with that of the value of n. So I hope this is clear for a given elliptic curve. Now coming to elliptical cryptography, so how you are going to do is public elements. These are public elements which are known to everyone in the network. So how you are going to have this public element means EQ of A comma B, which is the elliptic curve what you are going to take, and n, this is a number of points that will be there on the elliptic curve, and G is a generator point, and PA, PB are public key of A and public key of B. So these are the things which are available to the network. So hacker will get this information very easily, and this finding out NA and NB is the private elements, and these finding out these particular private elements in the elliptical cryptography is what we call as discrete logarithmic problem on elliptic curves. Right? So coming to elliptical cryptography, so how we are going to provide this encryption and decryption mechanism on elliptic curves is here as per the given data, EQ of A comma B elliptic curve is ready, G generator point is ready, and n number of cycles that the particular points on the particular elliptic curve. And now A and B are sender and receiver. The A will be having one private element which should be taken less than n. So n is, for example, if you consider this particular elliptic curve, so n will be less than 28. So you can take 3 or 5 or 7, 11, whatever the values that are less than 28. So A will be taking NA, which is the private element, and B will be taking NB, which is the private element, which is also less than n. So these two, I hope you understood how the private elements are considered. It should be less than n. And now how you get the public element? That is PA is equal to NA into G, and PB is equal to NB into G. So NB is the private element and G is the generator point. In the same way, NA is the private element and G is the generator point. So I hope you understood how to get the public key elements of A and B. And now the public elements are visible to everyone in the network. That is why B is sharing his public element to A, and A is sharing public element of PA to B. So how we are going to calculate the key is secret key. This public element, so PB is given to A, so he will be using his own private element here, NA, so NA into PB. In the same way here, PA is given to B, so he will be using NB into PA. So if you solve this, both the keys are same. That is NA into NB into G, NA into NB into G, where NA and NB are secret. So finding out that NA and B is called discrete logarithmic problem. This is very difficult problem. While you are looking at the formulas, it looks pretty simple, but when coming to execution part, it is very complicated. That finding the DLP is the ultimate motto of this elliptical cryptography. Right? This is what we call as discrete logarithmic problem on elliptical. Now, coming after the keys are ready, how the encryption and decryption is done. So encryption, PM is a message, okay, message point. So you are going to take any of these particular 28 points, if you consider this elliptic curve, as one message, and you are going to generate a ciphertext with 2 points. That is K into G. What is G? That is a generator, and K is a value that is chosen at the time of encryption by A. So A is wants to send some information. So A will be using K, and he will be using the KG is 1 point, and PM, that is the message point, plus K times of PB. So what is PB? That is a public element of P. That is the ciphertext point. So once the encryption is done, this particular encrypted message will be transferred in the channel. And that channel, the receiver will be trying to decrypt it. How he is going to decrypt it is because only NP is known to only D. Right? Only D knows what is NP. So he will be using the D into the first point in the ciphertext. He will take the first point and he multiply it with his private element. So he will get A, G, and D. Is it clear? Next, take the second point in the ciphertext and subtract it with the first step. So Pm plus KB, you are taking the second point, subtracting the first point, and what you are going to get? Pm. So this is the plaintext that you are going to get. So this is how the elliptic cryptography encryption and decryption is done. Right? Now this point is finding out the discrete logarithmic problem. So how to find out the discrete logarithmic problem? So since the equation is there, elliptical equation is there with that of generator point, N, public key or unknown. These are all the things which are known to the cryptography list. So these things are known to the cryptography list, and the cryptography list is interested to find what is NA and NB, which are the private elements of A and B. So this is what we call as discrete logarithmic problem, right? So this is what we call as discrete logarithmic problem. So how you are going to identify this discrete logarithmic problem is by these steps. So the step number 1, you have to calculate M. So how you are going to get M is M should be greater than N. So for example, here in this case, N is 28. So root 28 will be something around 4.38. So it will be 5. So M is equal to 5. So this is how you are going to calculate step 1. And step 2, you multiply M into G, which is, so what is M? 5 into G. So what is 5 into G? What is G? Is a generator point. That is 5, 1. So 5 times of G. So you can see that 5 times of G is 9, 16. So it will be 9, 16. After that, you generate for I is equal to 0 to M minus 1. Compute I into G. So for I is equal to 0 to M minus 1, it's 0 to 4. Right? So I is equal to 0, 1, 2, 3, 4. So what are the values that you are going to get? Right? That is, what is it? Ig. So that is I into G. So 0G, 1G, 2G, 3G, 4G. So what are 0G? 0G is infinity and 1G is 5, 1, because you can see 1G is 5, 1 and then 2G is 7, 12 and 3G is 19, 5 and then 4G is 17, 3. So these are the values that you are going to get as we have calculated for that. Next step is step 4. You have to calculate for J is equal to 0 to M minus 1. You have to compute, that is PA or PB minus this point. So how are you going to find out? If you want to find NA, which means user A's private key, then you have to use PA. If you want to know what is private key of B, you have to use PB. So here you can see again this step J followed by what are the J from 0, 1, 2, 3 and 4. So here you have to calculate, that is PA minus J times of M into G. So this is how we are going to calculate. So what is PA? So you have to calculate what is PA because encryption and decryption you have to use it. And finally, one of the point it will be saved, right? Whenever it is saved, you for example consider that 19,5. Are you getting it? 19,5. So this particular value, that is I is equal to 3, and here if you consider I is equal to 1, right? So here also if you get 19,5 after performing this operation. So here I is equal to 3, I is equal to 3 and J is equal to 1 if you get that. That is a matching point. Then you perform that in this equation, that is NA is equal to, what is I? 3 plus J is 1 times of 5 mod, what is N? 28. So it will be 3 plus 5 mod 28, which will be 8. Right? So identifying NA, which is 8, is discrete logarithmic problem. So these are the important steps. Actually, we are having a rough guess. NA we have not taken actually. So this is how the process starts, right? So if you perform some of the values as NA and PA and calculate as per the given steps, you can directly get what is NA and NB, which are the private elements of A and B. Right? Thank you.